So what about carboxylic acids, or acids with carbon and oxygen in them? We're going to look at a structural equation, and that's going to help us understand a little bit why they are acids. Where are the hydrogens coming from? Why, when you have acetic acid, we only lose one of the hydrogens, not all the hydrogens that are in that compound. So we take a look at what a... Oops, there, refreshed. We take a look at an example of acetic acid and what that actually looks like structurally. You're going to have a carbon, and this is why sometimes it's written as CH3. It helps you look at its structure. A carbon bonded to 3 hydrogens to another carbon chain. That carbon is going to be double bonded to an oxygen who has his 2 sets of lone electrons, to another oxygen, to a hydrogen. So this is acetic acid. We've talked about them a lot. It's the first time you've seen them as a actual structure. Now there's a bunch of hydrogens here, but the question is, which hydrogen is it going to be easier for water to pull off? So if we have a water molecule coming in, he wants to pull off one of these hydrogens. So here's this water molecule with those 2 big old electron pairs. He's going to try and pluck a hydrogen off this molecule to make that hydronium ion. The question is, I'm sure you can guess by me drawing him over here, it's going to be this hydrogen out by himself. Why not these, though? Why can't water take them? And if we look up electronegativities, we find that carbon and hydrogen are extremely close to each other. They're different by like 0.3. It's not a very polar bond at all. So there's actually quite a bit of sharing going on here between these this carbon atom and these hydrogen atoms in terms of electrons. But if we look at this guy, this is an extremely polar bond, pushing the lines of being ionic. And we were looking at a difference, a quite large difference of about 1.4 in electronegativity between an oxygen and a hydrogen. That's why water has such a polarity to it. It has those same oxygen-hydrogen bonds. So this guy, yeah, he's sort of getting some of these electrons, but they're spending 90% of their time over here with oxygen. So when he sees just a free pair of electrons that this oxygen's offering him, it's going to be very, very easy for him to go ahead and say, hey, it's a lot sweeter over here if you join me. And then we end up with our acetate ion and our hydronium ion. This being the part that makes the solution acidic. Long pause. Anyhow, the acidity is enhanced by replacing the H's with more electronegative elements. So if you had this, instead of being a CH3 at the beginning, and you had an element that looked like CCl3, then we're going to have even a larger pull to that left side in the way we drew it. Of course, it's in 3 dimensions, but a larger pull of electrons to the left side of that compound, and it's going to allow for that hydrogen to be removed even easier. So that's what's going to happen down here. The more H's that get replaced, the more they're going to be removed. I'll draw an example so we can see that, because I don't know if you're going to be able to visualize it. The only difference between what you're going to see on the screen here and what we just saw is that instead of H's, we are dealing with chlorines. So that same picture would be the case, except for these would all be chlorine bonds, and I'm just going to say ... for what the rest would look like. So overall, the electrons are going to spend more time in this area of the molecule, and that poor little hydrogen that's out here, he's rarely going to get to see any of them. Right, we're getting close to being done.